Colloquium speaker, Professor Ravi Sheth. At the outset, let me say we have been trying to get him here at IUCAA for forever, ever since I joined at least, and this is probably the first time that we've managed, so we're very happy to have him here. Ravi is an expert on all things in large-scale structure.
Recording in progress.
PhD from Cambridge and Bill Zaslow, followed by postdoctoral stints at Berkeley, then MPA in Munich, at Fermilab in Chicago, and then he took up a faculty position at the University of Pittsburgh for a few years before moving to the University of Pennsylvania, where he is currently as well. And in the middle, he spent a few years also at ICTP in Trieste, coincidentally right around the time that I happened to be a postdoc there, and that's where we overlapped for time. And he has worked on really almost every aspect of statistical and large-scale structure that you can imagine. He has pioneered or significantly to a number of concepts and ideas in large-scale structure, as well as tools that people are still using very actively. So many of you may have heard of the Sheth mass function, for example, the halo model of large-scale structure, assembly bias, which used to be a very technical thing, but have now become an industry of its own, and many other things. And one thing where we also had some work together was the excursion set approach, which is one of the last remaining analytical models for understanding large-scale structure, which has now become a mostly simulation-driven regime. So today he's going to tell us about the baryon acoustic oscillation feature and how one can use it in cosmology. So, over to you.
Thanks, Asim. Great pleasure to be here finally. The fourth has always been mine, and not making it. And I must say, the greatest highlight of my time in Trieste was meeting Asim. I'm glad that we managed to collaborate. Okay. So I thought I'd talk a little bit today about this method that people use for measuring distances on very large scales. It's a complementary method to estimating distances using supernovae. The one that uses supernovae is using something like the luminosity redshift relation. This one uses the angular diameter relation. However, it also uses it doesn't use, but it can be impacted by or hurt by the growth of structure. So not just the geometry, but the gravitational growth of structure. And so what I wanted to do was to sort of set up a little bit how this method works, and then the stuff that we try to do to mitigate the effects of gravitational growth. So I realize there's the summer school going on just now, and so I'm not sure how much of the CNB background some of you will have had, so ask me as I go through. I have a little bit of introduction to the CNB first. That's because one way to think of this method is it's a way of taking the CNB physics that we think we understand and seeing how it's reflected at later times in the universe history. Yeah, so the CNB is when the universe was about 1,000 times smaller than it is today. That's when those photons were released. That's when the photons started traveling through the universe. And we think that something about the patterns that they had then is imprinted in the structure of galaxies today and gas today. So I'll go through a little bit of the motivation first before I go through a little bit of the complications that we have to deal with to actually make this work. So a bit about the CNB. Yeah, so the CNB is this time when the universe was initially very hot, so the photons travel and they scatter off electrons that are, because the universe is hot, the hydrogen in the universe is ionized, and so they scatter off the free electrons. The universe expands, it cools, eventually the electrons can get caught by the proton. At this point, the photons no longer scatter off any electrons. They have to have just the right energy. The photon has to have just the right energy to excite the electron. All the other photons do nothing. And so suddenly the universe becomes transparent. Okay, that's the very crude CNB statement. And so the question is, how do inhomogeneities in the universe at this time get imprinted on the sky? So the idea is that we'll have photons that are moving around, they scatter, 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 and then the universe becomes cool enough. And once they become cool enough, then the photons can travel in a straight line. Right? So this is what this animation is showing, is some photons move around, they scatter, then the universe became cool, so they could go in a straight line. They could have gone in a straight line in any direction. We're looking at a few photons that end up coming towards the center. So there are two things that you can see, is that you have photons that will travel, and if you want, by moving and scattering around, they will make everything the same temperature of order the patch that they could scatter around to. And then they go in a straight line. So there's a characteristic scale, which is more or less the age of the universe at the time they stopped scattering, times more or less the speed they were going, which is the speed of light, but not the speed of light because they don't go in a straight line, they scatter. So it's roughly the speed of sound. So the patches will have that scale. Okay? Now the question is, how does that physical scale in 3D get converted into a scale on the sky? And so to try to visualize that, there's a very beautiful website for going through the physics of the CNB. So I've just taken one animation from there, but there's a whole bunch of very, very nice ones. So this one is saying, let's imagine that you have a density wave near the universe. And so you have this fluctuation, and the fluctuation is hot and cold and hot. So that's what this thing is supposed to be showing you. And so now you can ask, when the photons are released for the first time, when you get the pointer, when the photons are released for the first time and they start traveling in a straight line, then immediately after that, you will only be receiving photons from very nearby, because they have not had time to travel very far. So immediately after the photons are allowed to travel in a straight line, if you look and you receive photons from different directions, you will receive all the photons that are the same, because everywhere around you is the same temperature. But suppose you wait a little bit longer. You wait a little bit longer, now you can receive photons from slightly further away. So now those photons that you receive from slightly further away, they're from a slightly bigger distance. And now you can probe that surface. That surface probes the fact that there were hot and cold regions. And so at later times, that surface is very far away from us. And so it has probed many crossings. And so you have a pattern on your sky, which is a pattern that was present at that early times. And it will appear on your sky as hot and cold patches on your sky. This was from one sine wave perturbation, but you could have had many different sine wave perturbations of different wavelengths in different directions. And the complicated sum of all those waves will be some complicated pattern on the sky. And that's what we see as the CMB today. If we wait till tomorrow, that CMB sky will be a little bit different because that surface will have moved a little bit further, but because one day is very small compared to 14 billion years, it's not effectively very different. If we wait 10 billion years, then the CMB sky will look. Okay? So the only physics in here is the photons that scatter, and then they stop scattering. Okay, so it's well understood. And this is interesting because we know the temperature at which they're going to stop scattering because we understand hydrogen. And so that means we know what the typical size of these spots should be. So that corresponds to how the photons scattered around before they went in a straight line. So we know that size. And so the way the CMB gets used to do geometry as a test for the geometry of the universe is to say, we know the size of these spots in kilometers. Given a model for the universe, we know the distance to the time when this happened. And so now we can ask, if we know this distance and we know this size, then what the angle appears to be depends on the curvature. So if the universe is flat, then the angles will sum to 180 degrees. If the universe is closed, the angles will sum to more than 180 degrees. And so the same length at the same distance from us will subtend a larger angle. The universe is closed, the smaller angle, the universe is open. And so the idea is we understand the physics that makes this length, this standard rod. Given a model for the universe, we know how far away the rod is from us. And so the curvature of the universe will determine whether the spots appear big or small. And that's the CNB probe of the geometry of the universe. Right? So this has been very useful in cosmology. And the question is, can we use it for more? So the idea, the question we're going to ask is, the galaxies which form much later than the CNB, they carry some memory. That's the idea. So the idea is what? The idea is that the photons were initially banging against the baryon, banging against the electrons drift, they get pushed. And so we're going to imagine an initial spike where we had more photons, more baryon, and more neutrinos, and more dark matter, at one initial spike. Now the photons will start going up, but there are more photons here than here. Photons are going move out, they'll hit the electrons as they try to go up, they push the electrons. As they push the electrons, so that's some electrons get pushed out. By definition, they don't interact with dark matter, so dark matter remains, spike remains there. But the baryons, they get pushed out. And they'll get pushed for approximately 300,000 years, which is about the time when the CNB, the universe becomes cool enough, hydrogen becomes neutral, and the CNB photons move in a straight line. So it's really about 380,000 years, so about 400,000 years. And to set scale, 300,000 years at the speed of light, 300,000 light years is 100,000 megaparsecs. And that's 100 kiloparsecs. This is 100 kiloparsecs at a time when the universe was 1,000 times smaller than it is today, because the redshift of the CNB is 1,000, because the temperature of the CNB we observe now is 2.7, and we think it started out at 2,000. So that ratio is 1,000 and a bit. So if I take that length, I take this ratio, and I multiply by this length, that tells me how much this length got stretched because the universe expanded this many times. And so that is a length which is 140 megaparsecs. That's the length that those spots in the CNB, that's the length they should be today. Right? That's the radius of this circle that they should be today. Of course, there was not one spike. There was a collection of spikes. Each one of these, the photons went out. Around each one of these, there is now a sphere of radius 145 megaparsecs. Okay. So there is some complicated collection of spheres of radius 145 megaparsecs of small amplitude compared to the spike in the middle. So it's going to be difficult to see by eye, but statistically we should be able to see. Yeah? So that's the game that people are playing. Is they're trying to see this slight excess of baryon that are making spheres of radius 140 megaparsecs today. Okay, so this is the cartoon, right? So the cartoon is there should be a spike of everything and then this extra circle of 140 megaparsecs. Of course, it's a cartoon, right? It's not quite right because, so the idea is what? The idea is that from those baryons, that baryons means hydrogen gas, from that hydrogen gas, you're going to make stars. And so the idea is that those stars are what we are going to see today as galaxies. And so we should see, around any clump of stars, we should see a shell of other stars. Around any clump of galaxies, we should see a clump, a shell of galaxies. So in a galaxy survey, we should see the physics of the CNB. And the thing that's wrong with this picture is that we have some galaxies that are close to us and some galaxies that are far away from us. Around each one of them should be a circle of the same size, 140 megaparsec. So the guys that are close to you should be a big circle, will appear to you as a big angle. The guys that are far away from you, they should appear to you as a small angle, a small circle. So you should see something more like this. Yeah? You should see, you are the observer over here. If you look in the sky, you should see big circles, small circle, CNB. That's what you should see. Of course, again, it's going to be difficult, right? Because now they are the collection of all these different circles of different sizes. But now you can try to pick galaxies that are all the same distance from us. And so you pick only these. So around these, you should have circles all of the same size. So those circles all of the same size are the same physics as the circles that are here. It's just that these circles, they got stretched to be this big. Because the universe expanded, it got stretched to be this big later. And so now we can measure the geometry of the universe, or we can measure the angular diameter distance relation at many different distances. Not just the CNB, but any distance in between, all the way to us. So that's why it's such a nice probe, because it's the same physics applied at many different epochs in the universe. That's the attraction. We can end in 10 minutes. Okay. I'll speed up.
Sorry, I have.
Yeah, sure.
How do you know that these circles are like the things around them are actually isolated? What overlap?
That's good. So they may well have overlap. So because that cartoon with one circle is this picture, but really it's this picture. So really there's a bunch of overlap. Okay? So really it's a much messier thing. There are many circles all overlapping with one another. Okay? So it's not something that we will look at the sky and see. Right? We'll have to do some statistics to measure. So we'll do that in a second. Okay. So the first point to be made is that this is like vastly exaggerated, right? We have the spike and then the shell, and the amplitude of the shell is small compared to the main spike. Okay. And so what that really means is that around any collection of galaxies, there's only a tiny excess that makes the circle. And because this excess is on a circle of size 140 megaparsecs, you need a survey that will be of order that, if not 10 times that size, to see many of these circles, to make this measurement. So you need, we couldn't until now measure enough of the sky to have enough volume to play this game. So that's why we needed large surveys. Now we have the large surveys, so we can do this. And so this is an estimate of the current big spectroscopic survey. It's called, I always thought it was called BASIC. The large survey, dark energy spectroscopic instrument. And we are the observer here, and then there are, one set of galaxies that they've selected in a certain way here, another set of galaxies that they've selected out to bigger distances, and then these are quasars. Okay. And all told, they will have nearly 100 million objects. So they will have lots of them. And so they can look at the galaxies in this shell and try to see the circles that I was talking about, or they can look at the galaxies in this shell for the circles. So they will gradually map the angular diameter redshift relation and see if it is consistent with the GR lambda CDF. Okay. What do you actually do? So what you actually do is you sit on one galaxy and you count how many galaxies are within 150 megaparsec, 140 megaparsecs. Then you go to the next galaxy and you count how many. You go to the next, you count how many. So you have however many you counted. And then you say, okay, but what if the galaxies were just scattered at random? So then you would say, well, there was no clustering at all. If there was no excess, what do I expect? So that should be 4 pi r cubed over 3, the volume of a sphere times the number density of galaxies. That's how many I should get inside a sphere. If I want a shell, it should be 4 pi r squared dr. The shell. Okay? So you know what you expect. So you take what you counted, you divide what you expect, and you ask, how does this differ from 1? You subtract 1, you ask what is left. That's your signal. Okay? So the ratio with respect to random minus 1. So that's what is shown here. The ratio with respect to random minus 1. And then, because it's a very small signal, so this thing psi as a function of r, this thing would be the thing that I was talking about, the ratio with respect to random minus 1. And this number is very small, because remember we said the peak will be like this with a small extra bump. So to enhance, just to be able to see it more clearly, we multiplied everything by r squared. And that means you multiply this, the value here, by 100 squared. So you get 10 to the 4 factor. Okay. When you do that, you can see this nice bump. Okay. Don't worry about the bump here. That's a little bit because you have some curve that is going up and you're multiplying by r squared and the small r is small, so you depress it. But this one is the BAO feature, the baryon acoustic oscillation, the CNB feature. It looks like it's at 100 megaparsecs because this is in units of 1 over h. H is 0.7, the Hubble constant is of order 0.7. Some of you will be doing there's some tension, whether it's 68 or 70. For this purpose, although the precision is good enough to address this question, for the logic of the approach, I won't get into that. We'll think of H as 0.7. And so 100 over 0.7 is the 140. So it's at the right scale. Just the right scale by I. Then we get into, we're trying to do precision cosmology and how do we measure this precisely. But that you see it in the data is encouraging. So we have surveys that are big enough to now see this small feature. Okay, one little bit of jargon. Most of my talk, I will be doing what's called the correlation, the pair correlation function, which is the thing that I described. You sit on one object and you count how many others are within a distance r. A lot of the field works with the power spectrum, which is the Fourier transform of this guy. So the power spectrum is something that looks like this. This is k, and this is the power spectrum as a function of k. And it's the Fourier transform of this guy. And so to get some intuition, the way to think of this is the following. This curve is basically, it's like a smooth curve with a delta function. So the smooth curve, the Fourier transform of the smooth curve will be some smooth curve. The delta function, if it's a delta function at 0, that is a constant when you take the Fourier transform. In this case, the delta function is not at 0. So the Fourier transform of a delta function not at 0 is J0 Bessel function, sine kr over kr. And so the sine kr over kr is what's making these wiggles. And so there's a slightly confusing thing that happened, which is this peak is more or less the scale that we expect, the physical thing. This measurement, the signature of the measurement, is not the amplitude of the oscillations, but the wavelength of sine kr over kr. So it's the wavelength, how far do you have to go in k from one bump to the next bump to the next bump. Okay. So let me try to illustrate that there. So here what we've done is, or what the field usually does is they divide out by some smooth curve so that it's easier to see the sine. Okay, so now you can see the oscillations. This is when they first started taking data about 10 years ago, and this is about 5 years ago. Okay, so you can see that you're measuring this with higher and higher precision, and it's the sine k over kr kind of thing. Okay. With a little bit more than that we'll come to in a second. And so this wavelength is the BAO scale in Fourier space. Okay? The scale of the delta function is the BAO scale in real space. Okay. So I said we can do this in a galaxy survey, but this should be true for any set of baryons. And so this is, you have photons coming from a quasar. Photons are traveling to us, the observer. So the quasar had some spectrum. And then as the light from that quasar travels to us and passes through gas along the line of sight, that gas is baryon. So those baryons do some absorbing. If I can run this guy again. And so each time it passes through the gas, you see some gas, some photons are absorbed. So we're gradually saying, as the photons travel, the universe has expanded, so all the wavelengths have got redshifted, so they've all got longer. So that's what you're seeing, is all the wavelengths are shifting longer. And now what you're seeing is that there's this forest of lines, the Lyman alpha forest, which is the gas that got to absorb the photon. And so the gas, this is a map of the baryon in the universe along this line of sight, or along another line of sight, or along another line of sight. You have many different maps of the gas distribution along the line of sight. And so now you can say, well, as you saw here, there was some distance that the photons travel. So that means that these wavelengths, they correspond to some number of megaparsecs. So that means really there's some number of megaparsecs here. And so I can ask, if I sit on one cloud of gas and I count how many other clouds of gas on this side, when I count at 150 megaparsecs, there should be a slight extra. Because the arguments that we made so far didn't say that the baryons had to turn into clouds. Should work. So even in the Lyman alpha forest, we should see the signature. And so that's the signature in the Lyman alpha forest. It's a little bit noisier. We don't have 10 million lines of sight with something fewer, but you can see the peak. And so the nice thing about this is that you can do this with multiple different probes, not just galaxies. You can look for this feature. Here you're seeing the feature when the universe was, 3 times smaller than it is today. With the galaxy surveys, we see at redshift 2 or at redshift 1, universe was twice the size of it. And so we really can map it out. What do we actually measure? Well, we're really measuring a sphere. And so the sphere means that if you're looking, then you're seeing 2 angles and a width in redshift. And so the sphere has angular diameter distance and redshift distance across two components across the line of sight, one component above the line. That's the thing that you're really measuring. Okay. So in practice, what do you do to make those plots that I showed before? Because in practice, you're measuring some angle and some redshift for each galaxy. Whereas the plots that I showed you, they have some distance in megaparsecs. So you have to convert the angles and redshifts into distances. So you assume a cosmology. Having assumed the cosmology, now you can convert angles and redshifts into distance. Now you check if the distance scale came out to be the one you follow. If it didn't come out to be the one that the CNB told you it should be, then you say I should change my cosmological model. Principle, that's what you should do. Keep track to find. Okay. But you can be a little bit more innovative because this seems slightly circular. Right? You chose a cosmology to check if that cosmology is right. Okay. So you can ask, can you do something else? So you can ask, maybe I can just measure the distances in redshift. So here's a plot of that. The correlation of redshift distances, and you can kind of see a bump there. But this bump is a little bit difficult to measure. It's a little bit broad. And so people have started thinking about this, but the significance depends, the size of the error bars depends on how broad we make the bin in redshift. And remember, bin in redshift means circles of different radii. And so circles of different radii means you smear out this thing. And so you need a narrow bin in redshift to get circles of one size, but then you have few galaxies. And so then you have big error bars. And so currently people are trying to play this game, but not much. The other thing you can do is you can just try to play what is the distribution for angle. So now you say, I'm not going to measure across the line of sight. On the sky, I'm going to just measure the angular size of the circle. But again, you have to pick galaxies of some redshift, some more or less fixed distance from you, so that the circles are more or less the same angular. Okay? So here, just to illustrate, taking redshift of 0.4. And for the redshift of 0.4, we say, let's concentrate for now on the solid line. So if the width is narrow, then you get a nice peak. But if the width in redshifts is a little bit wide, then you degrade the signal. And you have to make it a little bit wide to have enough galaxies to do the measurement in the first place. The wider you make the bin, the more you smear out the signal. And so the angular game is also hard to play. And so that's why people prefer to convert to do this slightly circular thing. But it's worth bearing in mind that this can be done. Right? As we have more and more objects, we will be able to make these bins narrower. And we can start trying to play this game in angular space and in redshift without doing this slightly circular. We can get around the slightly circular thing as follows. So this is an idea that goes back before people were thinking about video. It's called the Alcock-Paczynski test. And so this idea is, if you have something that is a sphere, it's physically a sphere, then if you measure angles and redshifts, and you try to convert using angular diameter distance relation to convert the angles into a distance, and the Hubble distance relation to convert the redshift into a distance, if you guess the wrong cosmology, you will not turn the angles and redshifts into a sphere. You will turn it into something warped. So the idea is that you should keep changing until you get a sphere. And so here the idea is, yeah, we have spheres. We know that there should be these shells. That should be spherical shells. And so we should keep changing angular diameter distance, Hubble constant redshift. We should keep changing those, change omega matter, omega lambda, till this thing is a sphere. And once it's a sphere, we can measure its radius. Okay? So that's the way the game is played. So you play the Alcock-Paczynski game to turn your measurement into something that is round, something that is a sphere. And once it's a sphere, you measure its radius. And you say, is it the one that the CNB predicted? Yeah. That's a nice game to play. But the problem is that our observations are in redshifts, not of position. And so I've underlined here redshift space distortions limit the scales to which this can be done. Okay, so let's talk a little bit about that. So before the redshift space distortions, the cartoon of how this game is played, right? So suppose this is the right answer, then what we do is we take the angles and redshifts, and we guess one cosmology, or maybe we guess the redshifts too stretched, convert them into this, or we guess the angles too much like this. So we have something that's not round, we have something that's not round, and then we get to the right answer. Right, so we fiddle this around until you get the sphere. Now for the redshift space. Unfortunately, we measure redshifts, we don't measure positions. And so the redshifts mean that the redshift that you observe is the distance with a peculiar velocity. And so on here, we're starting out, there's a number that counts off how important the velocities are. And so when everything looks like single dots, that's when this number is 0. And then as we up this number, that's upping the influence of velocity. The bigger the velocity, the more structure you start to see, right? You see these stripes that sort of point towards the middle. The observer is supposed to be in the middle here. So you can see that these things are changing the positions of things by the redshift space distortion. And so, if I imagine now that I had a circle, that circle will now get moved around because of all this striking spike stuff. And so we will look at that in a second. And we will have to be careful about this effect for the following reason. So let's imagine that I started with a sphere. Okay, so I started with a sphere. And suppose this sphere is slightly overdense. If it's slightly overdense, then gravity is going to make it collapse. If gravity makes it collapse, then what happens is, here the arrows showing gravity is going to make everything collapse to 1%. Suppose you are an observer over here, and you're looking at this thing. Then when you measure the redshift, so instead of the position, instead of seeing something round, you will see this, but because it's moving towards you, you will think it's not so far away from you. You'll give it a smaller edge. This one, because it's moving away from you, you will give it a bigger edge. You will see a bigger edge. So this round thing will look to you like it is squashed along the line of sight. But if the way we were going to use the Alcock-Paczynski test was to say, I'm going to reconstruct something to a sphere, that's only correct if it should be a sphere. Now we're arguing that if we look at a dense region or another dense region, we will get ellipses. It complicates the use of the Alcock-Paczynski test. So we must be able to account for the fact that the observations are done in redshift space, to be able to do the Alcock-Paczynski test, to be able to make a round circle whose radius we can measure. Okay? So these two things will go hand in hand, accounting for the fact that we make a measurement that is redshift space distortion. So here again is the cartoon. So the cartoon is the infall. The coherent infall will make a sphere into an ellipse. Right? That means that we now, because redshift space distortions are correcting distances along the line of sight. They're not affecting distances across the line of sight. So now if we're going to count up pairs of galaxies, then we will be careful to distinguish between pairs, the separation across and the separation along. So before, when I showed you a correlation function, so the number of pairs divided by the random, that was like a 1D curve. So now we're going to be careful. We'll make a difference between the separation across the line of sight and the separation along the line of sight. And people usually, they cheat. The actual measurement is just a quadrant, and then they turn it into a butterfly by just mirroring everything. And what you can see is that the nice round shape is now squashed for the reason that we described. So that's that on large scale, more or less, if you're sitting on a galaxy, you're sitting on a slightly overdense region, and so stuff is going to collapse onto you. And so there will be this squashing along the line of sight, and no squashing across the line. So this is the level of effect we have to be able to account for, to get rid of, to understand, in order to do the Alcock-Paczynski thing, and in order to do the BA simultaneously. Right? So here is now a measurement in some simulations of the same kind of thing. Okay? And here, to sort of illustrate the effect, I'm showing you the same measurement that I had before, where there are no redshift space distortions, so at the start of the talk, where I just showed you the bump, but now shown in the 2D plate, 2D configuration. So let's look just at the left-hand panel. And this is in redshift space. Real space and redshift space. So we want to we want to account for this squashing. This is the thing, small ellipse that started from this thing because of the redshift. Okay. These are just the complications of what we observe at redshift 0 that are more or less understood, but we should account for. There's another question, which is, the CNB was made 14 billion years ago. Those 14 billion years, gravity made things move. How do I know that that circle, that sphere that was 140 megaparsecs then is still 140 megaparsecs today? After all, to get the redshift space distortions, to get this from this, we made this argument, right, that there will be some kind of squash. And so we need to be sure, we need to quantify how much squashing happened, how much shrinking happened in the 14 billion. Okay. So this panel, which is the same in both, okay, this panel is showing you the real position from which these objects started in the simulation. And today they ended up being here. Today they ended up being here. So on small separations, you see this is much different from this. But on large separation, it's more or less the same. And we want to be sure that it's the same to within a percent. Okay? That's what we're trying to do. And what we're really trying to do is, our observations are going to be of this. And the thing we want to do science with is this, what they started. Okay, so we need some way of taking our observations and taking them back to something like this. So we want to be sure that the BAO signal, the galaxy distribution today, can somehow be mapped back to what it started out as 14 billion years. Here's a nice simulation that was done by Nikhil 10 years ago. Normally when people do a simulation, they'll have a whole bunch of particles that are all equal mass, that gravity goes to work and makes them cluster. So that's the slight gray thing that you see in the background. As time goes on, gravity has made cluster. It started out smooth. What Nikhil did was he added a whole bunch of particles on this red circle. Okay? Extra particle or mass if you want, but you still have, there's no fake gravity happening. And he solved for the evolution, gravitational evolution, to ask, if I have such a sphere, how does it deform in 14 billion years because of gravity? So what you can see is that it deforms, but it doesn't shrink very much. Maybe the center was offset slightly. Maybe it got a little bit thicker. It's no longer a nice neat boundary. But it did not shrink. Okay. There is one important thing that was first pointed out, not in the context of BAO, because this paper was before that, but the important thing is the following. The nice, clean circle gets smeared out because things have moved around in those 14 billion. And you can see, that things moved around. Nothing moved from this side to this side. Nothing moved 100 megaparsecs. Things are moving 10 megaparsecs. And so what is happening is this shell is getting slightly smeared out. And that's what is shown here. The thing that started out as a fairly sharp shell has gotten slightly smeared out. Okay? Think of this as before I said delta function. So now this delta function got broad. And so our problem is to unbroaden the delta function. One way to say it. Yeah? So there are going to be two ways we can think of this problem. One way we can think of this problem is to say, I want, they were doing it with one circle, but really there were all these different circles, right? So I want to move all the particles back to where they were initially. That's one thing that I could be trying to do. That is called reconstruction at the field level. You're reconstructing the entire disk. The other thing you could do is you could say, I'm not interested in reconstructing all the details. At the end of the day, I'm going to measure the pair correlation function. And the pair correlation function I showed you before has this nice bump. That bump was like this thing, right? And then there was just a smooth thing like this. So I want to reconstruct this thing to make it back into this thing. So I just want to reconstruct this statistic, not the full field. Much less information, maybe much more efficient. Okay? So there are these two approaches. So the idea, right, that the flows have moved everything to sort what was initially nice shells and has made them blurred out by a blurring that is off order in lambda CDM, about 7 microns. At redshift 0, less at higher redshift, because there was less time for things to move. And so that's the idea, right? You started out from this nice bump, and it got smeared out to this one. And roughly speaking, if you think of these as just random motions with some Gaussian distribution, the RMS of the Gaussian is 7 megaparsecs. Then what you're doing is you're taking you're convolving the Gaussian bump with a Gaussian. You convolve a Gaussian with a Gaussian, it remains Gaussian, you just suppress the height. So that is what happened here. You took a Gaussian, you convolved with the Gaussian, you got a broader Gaussian. And so this got suppressed to this. But this is more or less what it was before. And so this simple model, that all you do is you smear with a Gaussian. Convolution with a Gaussian in real space. In Fourier space means you multiply by the Fourier transform of a Gaussian. And the Fourier transform of a Gaussian is e to the minus k squared times 3l squared. So this is this model. Okay, this model gives you this correlation, the simplest possible model. And the thing you can see is that the difference between the peak and the dip is gone. I mean, it's there, but it's harder to see. And so one reason for trying to go back to the blue is you're going to get bigger significance of the peak, bigger significance of the dip, so you will make a higher significance measurement of the distance scale. And so that's what we're trying to do, right? We're trying to do, we can say we're trying to measure this scale. And when it's a flat maximum like this, it's harder to measure the scale than if it's a sharp maximum. So how to estimate the scale? So I said crudely we'll estimate the maximum. But in practice, people do a little bit more than that. Okay? So let's go through. In practice, they're not going to just take the derivative of these measurements to find the maximum. The thing you would do mathematically, you have error bars, it's noisy, so you don't want to differentiate noisy data. So instead you want to fit, one approach is to fit some smooth curve and differentiate that fit. Right? Of course, you would rather do some kind of reconstruction, fit that reconstructed thing with a smooth curve, and then work with that. And so then the question is, what are we going to work with? Are we going to work with the peak scale or the dip scale, something in between? And so the way we usually describe this, we call it the VAO peak. And so that sounds like we're talking about this scale. In practice, you can do the following game, right? So in a simulation, you can measure the evolution of the correlation function as the simulation evolves. As the simulation evolves, the amplitude of the correlation, gravity goes to work, it makes the clustering signal stronger and stronger and stronger. You can try to divide out by the amount by which gravity should have enhanced the clustering. This is the correlation function divided by that amplitude. It's the jargon, the linear theory amplitude. So if you do this thing, then what you see is that the initial correlation function is that one. as time goes on, gets more and more smeared out. That's because the things moved 7 megaparsecs, 6, 5, 4, so. Okay. So this is the smearing out of the correlation function as gravity goes lower. But what you can see is that when plotted this way, the point that is in between the peak and the dip, they don't change. That position is pretty stable. Okay. So this is the thing we noticed a few years ago, that this position, the midpoint between the peak and the dip, seems to be remarkably stable to evolution. We have some understanding of that. But before I do that, here's a plot that shows this measurement for the dark matter in the simulations, but the things that we observe are galaxies. And so we can look at bias traces in the simulation. And what you can see is, we look at halos or dark matter, the scale is still special. And so it doesn't matter that you're looking at a special subset. You could do this for the Lyman alpha. Doesn't matter, the scale is special. And so that's a good standard ruler. Yeah, because this scale can, this height is certainly changing. Maybe the scale on which the maximum is happening is changing. Maybe the dip is changing. This one is stable. Here's sort of a test of that. This is how the position of the maximum changes from redshift 1000 down to redshift 0. How the position of the minimum changes from redshift 1000 down to redshift 0. Okay, so these change by a few megaparsecs. So it's a few megaparsec change on 100, so it's a few percent change. Whereas this position here, that changes by, so now we're plotting the position of the scale as a function of how much smearing, so as a function of time. So more smeared at late times, less smeared early, now is somewhere here. And there's two sets of symbols. You can take the midpoint of the peak and the dip, or you can take the inflection point. And they're more or less similar. They're both pretty stable. So those are good standard rulers. So if you want to measure the distance scale, this is the thing that's the most stable, without making some assumption about the detailed shape of this curve. If you are happy to make assumptions about the detailed shape of this curve, then what you do is you fit a lambda CDM motivated template to this curve, and you find the best lambda CDM template. So that's what the field will do. We do something simpler. We just find that linear point. And we have some understanding of why that's good, so you can ask me later, because I'm late. So the linear point is stable, we understand why. And so we will use that to quantify the length of the standard chord. So now what we need to do is we need to fit the data. So we can fit the data, and the model we're going to use. So I want to do an approach in which I'm not going to assume the lambda CDM model is right. So I'm just going to fit some polynomial to the data. I'm going to start out and I'm going to assume that the initial curve, the dashed line before, that guy was a polynomial. The solid curve that I do observe, that guy is smeared by a Gaussian. But it turns out that if you do the convolution of a polynomial with a Gaussian, you can write that analytically. So what that means is that if you fit the shape that you get from convolving this Gaussian, this shape with a Gaussian, then these fitted coefficients, when you fit them to the nonlinear shape, and then you plug them inside here, they'll give you the reconstructed shape, what the correlation function started out at. And so that's like reconstructing the signal, rather than reconstructing the field, reconstructing the summary statistics, reconstructing the 2-point correlation. So this is the sort of game that I played with Asim in the last year or so. It's trying to do reconstruction in this way. This is the sort of cartoon. These are the measurements. These measurements you fit using these funny functions, you get the coefficients for fitting the functions, then you plug those into the simple polynomial, and that reconstructs the red. The error bars are the measurements. The error bars, those error bars propagate to give the error bands, which are the red. And the linear theory that it started out from is the black. So you can see that you've taken the data and you've gone substantially back to the initial shape. And so now you can start measuring the linear point in this shape instead of in this one. So that's one game that we play. The other game we play is we try to reconstruct the field. So I'll do this very quickly and then stop. So reconstructing the field is the following. So you use a different idea, right? Because to reconstruct the field, we have a bunch of positions that we see today, where the galaxies are. We have to know where they came from. How do we know where they came from? So we say that we know that the CNB was smooth. The fluctuations in the CNB are 10 to the minus 5. So that means in this language, initially all the particles started more or less from a grid. In fact, the simulation that I showed you that Nikhil ran, it started out pretty smooth, except for that shell that was greatly exaggerated. So you can see, they start out smooth. So they really start from a grid. So what we're going to do, we're going to say that the particles today, which are the red, they all started from a grid, which is the blue grid. So what I want to know is which particle goes to which grid point, which particle came from which grid point. So we can do the combinatorics of all the possible combinations of matching red points to blue. But then we can say there is a special set, which is the one of smallest displacement, to take everyone back to the initial grid. So that means this went to this, and I don't have to think that this red one, so that this blue actually came from a red one over here, right? I don't have to do like that. I take the smallest set of this grid. That's going to be the model, and the nice thing about that model is that everyone agrees that the initial conditions were smooth, and in fact, people who want to test general relativity, who want to think maybe gravity is not GR, is modified gravity, most of those models also agree that the initial conditions were smooth. So most of those models would be consistent with this kind of approach for saying things don't move too far. This kind of approach is bad. Particles can move very far from where they start. If these were photons, this would be bad. Photons can travel very far. But mass particles don't travel very far. So it's a good approximation. The problem is there's many combinations that we can try. So how do we quickly solve this problem? So this is where big, fast computers matter. And so there's a nice new computer science algorithm for solving this problem. The computer science algorithm looks a little bit like this. Imagine that to the red points, I made what is called, the red are the clustered points, not on the grid. I made what is called Voronoi tessellation. So I separate the volumes into as the volume that is closest to this point rather than another one. So I do that for all the points. So I cover space like that. So Voronoi tessellation, all the cells are centered on the same particles, but the volumes of each Voronoi cell are different. The initial conditions say that my initial volumes were all the same because it was uniform distribution initially, that everyone was the same density, all the particles have the same mass, so all the volumes must have been the same initially. And that means that I have to move my cells around so that I can fit everyone to have the same volume. So I can start with the Voronoi tessellation. Then I can start saying I want to make the small cells bigger and the big cells smaller. I have to move the centers around. At the end of the day, I end up with something that is called a Laguerre diagram, where now all the cells have the same volumes, but now the positions have been shifted. So the shift in position is telling me where something moved, where it came from initially, to where it is today. That's the displacement that has smeared out the BA.
Is this obvious?
It's not completely obvious. So it's obvious if the motion is given by the Zeldovich approximation, this is exact. Okay. But if it were not Zeldovich, then it won't. Okay. And so where this really works well, so the Zeldovich approximation works okay on big scales, does not work okay on small scales. There's this thing called shell crossing. So if the particles cross each other, then you'll have some ambiguity in what particle should be with what breakpoint. Okay? So you don't want the shell crossing to happen. In the computer science jargon, it means you want the convex potential that is describing the space. Okay? So what the computer scientists have done is they have found this super fast way of solving this for this convex potential. Okay? So we're going to use that. And we're going to do one more trick, which is to say, in fact, we have bias tracers. Some might be clusters of galaxies, some might be massive galaxies, some might be low mass galaxies. So they all have different masses. A high mass galaxy came from a large patch initially, because it had to be uniform density. Small mass galaxy came from a small patch. And so now I want to solve the same problem, but now each one is given a weight depending on its mass. For dark matter, all the particles have the same mass, but I could put a halo catalog here, and each particle has a weight, which is its mass. And so now I make the Laguerre diagram associated, where I give each particle the weight. Okay, so here I take each particle has a weight, which is its mass. I can shift back the Laguerre diagram. And now I have the big cells, which corresponded to the massive guys, and the smaller cells, which corresponded to the lower mass. And I can do this reconstruction. So this way we can reconstruct the field. And this works very well. So I'll show you two slides that show you that it works very well. And then I'm late, so then I'll stop. I'll show conclusions. And if you're interested, you can ask me more details. Okay, so it works surprisingly well. Okay. Here is, so you know, there were all the particles in the simulation. We're looking at one particular quite massive halo, 10 to the 15 solar masses. This halo at redshift 0 are the blue points. In the initial conditions are the black points. So all these black points shrank down to be where the blue points are now. The gray region is the Laguerre cell, is the reconstructed shape of this halo, given the blue particle. But from the blue, then it said, you know, but somewhere here there was a halo, somewhere here there was a halo, I have to make the Laguerre diagram. So I reconstruct not just the centers of each of these patches, but actually their shapes. Right? And so, for example, it's not trivial. If I look at the blue, the long axis of the blue is like this. But the long axis of the reconstruction is like this. Okay? So it's doing non-trivial stuff. But it works quite well. So here's one where the center is quite offset from where it started. We're looking at it from 3 different projections. Quite offset from where it started. The green is where it started. The purple is where we reconstruct. We said, you know, this guy, the yellow, started from here. And it's very close to the right answer. So it will reconstruct the BAO very well. Because you have undone the motions that smear the BAO. Yeah. And so this works pretty well. And so then I have a bunch of slides showing you that it works very well. So I'll just skip that. And I'll just go to the conclusions, and then you can ask me questions if you're interested. Yeah. So this works very well. We reconstruct the initial shape quite well. Let's look at the optimal transport reconstructions of the correlation function. So this was in real space. This was the one quadrant that I showed you before of the whole thing. This is what we want to reach. We want to be like a proto-halo. These are the two versions of the reconstruction that we do. Okay? So the thing you want to look for is the nonlinear. This one is kind of fuzzy. It started out as something quite neat. And you want to see if the reconstructed thing is neater than this. That will mean that the BAO is sharper. BAO is very sharp. And it worked quite well, it didn't shrink, all that stuff. This is starting in real space. This is doing the same game, but starting in redshift space. Okay, so we started in redshift space. We started trying to reconstruct this. These are the reconstructions. Slightly fuzzier, but you know, they're not ellipses anymore. Right? So you've undone the redshift space distortion. And you're getting something that's kind of like a sphere. And then we can quantify this more. A bunch of those other curves are doing that. But this works remarkably well, especially if you're working with the bias tracers, because if you're working with halos, then the shell crossing is less of an issue. This is a little bit of detail about how we do the redshift space distortions, but then we put the summary. So in all these things, we would then measure the linear, because that's the nice system to measure. If you do a Bayesian thing, then you would say, well, you're measuring 1 point, so you will get larger error bars than if you are willing to guess a full shape. If you're willing to guess a template shape, then you will get better error bars. Okay, so it depends on how agnostic you want to be about what the shape should be, or what your error bar on the distance measurement should be. But these are all percent, sub-percent in the end. We can do a reconstruction by just fitting the 2-point function. So this is almost trivial. This is 0 type. Or we can do the optimal transform, where we try to reconstruct the field. And the virtue of doing that is we don't have to do only the 2-point function. We can measure many other statistics and see if we get information from them too. And so I won't talk about this here, but if you're interested. And then the final thing I have on here is synergy with this, with the kinetic SC effect that you can ask. So I think I should stop there and take questions. Sorry, I'm pretty late.
From the observation point of view, it seems that the density around the 145 megaparsecs seems to be important. So from the observation point of view, that the galaxy that we observe affects the number of points that we see around the 100.
You mean the fact that we're sitting on a galaxy, does that affect this signal? No. So that's a small enough effect. So some people have worried about what they call the 3-point function. They say, given that I'm on a galaxy, does it affect triangles where the other two should have been 145 megaparsecs away? Then the fact that there's something at the center matters. But that's a small thing, so people are not looking for it at the moment.
What is this dust model?
Okay. So there are other ways that people have of doing the reconstruction. So this optimal transport, which kind of thing, is a recent one, but there are others. The thing that is nice about this optimal transport is you make this assumption that you just have to go back to an initial grid. So you didn't have to make a model dependent thing that has some prior about how far everyone to go back to the initial grid. So that's attractive, but it comes at a cost. So one cost is that I had to the thing that is uniform, the uniform grid, is the total dark matter field. But I observe a galaxy survey. That's not all the mass. I observe a few bias tracers. In these BAO surveys that you say, what's the fraction of mass that is in the galaxies that you actually observe? It's like 20%. So the other 80% you don't observe. And so you can ask, that 20%, did they come from a grid? That 20% was a special subset. It did not come from a grid. They were clustered. And so when I showed you that the reconstruction works very well, it works very well because I had to make a model for all the stuff that I don't see in the survey. That's what I'm calling the dust, all the stuff that is below the resolution. And so then you can say, that's not nice. It's not nice, right? That I have to make some assumption about the stuff that I don't see. The one that is called G is, it's not quite that, but it's essentially this one. Is supposing I put this stuff, I just throw it at random. I say the stuff I don't see is uniformly distributed, which it is not, it's clustered. But suppose I say wrongly that it's uniformly distributed, and I throw it, I run the optimal transport reconstruction, and I ask what happens to the reconstructed state. That works quite well. Okay? So it works to the percent precision. So that's like the, so what did I need to assume to do that? I needed to assume this, that I saw 20% and I'm missing 80%. So that means I needed to assume a value for omega matter. The other thing I could do is W, is I can sit on each galaxy and I can do some cross correlation of the galaxy matter around it in a simulation. So then I can use that knowledge to say how much should be the clustering of the stuff that I don't see. Because I know the total should be the total clustering signal. So that means I have to guess the bias of the dust. So in addition to the amount of dust. So I have to guess how much dust, omega matter, how clustered is it, bias. The bias really means what's the strength of the clustering of every sigma k. So I have to assume those two. And so it's not really completely model independent. It's model independent, it's saying to go back to a grid is model independent. But then depending on how much information you want to add, you can get a better reconstruction.
Which one of these is the one which you consider the rightmost?
So, okay, so this is the redshift space distorted. This is the initial condition. So this is the correct answer. This is the target. This is what we want to be. So you can't do better than this. Then this one is the one where we put this very simple model for the dust. And that's just two different.
Visually, they don't look that different.
Yeah, they don't. And so, in fact, if I went slowly through the correlation functions, then the summary statistics are all.
And see, at small scales, they are
different.
center, they are quite
At the center, they don't.
yeah, but not at the beginning.
Not at the beginning. You're right, I see. So right here, you don't completely get rid of the quadruple on small scales. So this is the 2-point functions. It doesn't matter what model of the dust you use on BAO scales, but it does matter scales that are 20 megabytes. And so for the quadrupole, remove the quadrupole on large BAO scales, but on smaller scales.
So this has been applied to the actual thing. Sorry, I said.
Okay, so now they're currently applied to the redshift, to the DAISY survey. That's what finally is doing with Nikhil. Applying this to the DAISY.
Great, it's revolutionary clever.
But it's because these computer science guys have this nice code, right? Because otherwise it's an n-squared problem, it's a very slow problem. And then, I mean, it comes from this Zeldovich approximation. So there is a nice least action principle by people. And so there are people who have been trying to play this game with that least action principle. Crudely speaking, you can think of the Zeldovich approximation as everyone moved in a straight line. If instead I want to connect all my points, but they're connected by parabolas, that's the least action principle, which is not simple. So a parabola will have one more free parameter for each trajectory instead of a straight line. So there's a few more free parameters. You have a million galaxies, what that you have to solve for. Okay. And so that's one way people have tried to get around this convex potential problem. You can have total.
Okay.
So I was just wondering, in this year, a 2-point correlation function calculation, you also need where first random. So where do you get that?
So the randoms are, you have the geometry, there's a survey mass usually, there's stuff that is blocked out. So that is quite well quantified.
It's not from simulation.
It's not from simulation. Yeah. But it's literally you're throwing down points.
But in that case, you're bombarding the recipients of your.
Yes, correct. Correct. Yeah. So the survey has its shape, and you're throwing points at random inside that shape.
And how many pairs you will count will also depend upon how deep your survey is.
Correct. Correct. Yeah. So there's a nice thing that happens with these kinds of things. Yeah. Supposing that I reconstructed all the dark matter, Right now, I'm showing you only the bias traces. But suppose I reconstructed all the dark matter. If I measure the correlation function of the dark matter, if I reconstruct it correctly, I should get 0, right? Because I reconstructed to a grid. And so if I try to measure that guy, I get a 0 signal. So what did I do? And so there's a technical thing is true in structure formation, which is that the density in linear theory is the divergence of velocity. Velocity flows are making the density. And so what you have to do is you have to remember that. And you have to say that what you have from this optimal transport what you have from optimal transport is for each particle, you know, its displacement. Its displacement is its velocity, proportional to its velocity. So you want to do the divergence of the velocity, and the correlation function of the divergence velocity is the correlation, the linear theory correlation. That you can do without random. So you can save quite a lot of time.
I have a quick question. What guarantees that the stability of the linear point not just restricted to lambda CDM and that's why the.
So the stability of the linear point goes back to this slide that I went through quickly and said I wasn't going to discuss. So if it is true that something like the Zeldovich approximation is a good approximation in any theory of gravity, it's almost a continuity equation argument. Where you are now is related to where you came from. If that is true, so it's a fairly mild assumption, then this kind of smearing argument is a good argument. So long as the smearing is sort of Gaussian, then the Gaussian, I can expand for small k. Small k means large scale. So on BAO scales, we only care about small k. This is a 1 minus k squared. K squared is Laplacian, right? So Fourier transform Laplacian brings down the k squared. So I can ask, what is a Laplacian in real space? So I started out with a spherically symmetric function. I want its Laplacian. The spherically symmetric is the pairwise correlation function. If I've done the alcohol scheme and that's not correct, right? So the correct answer is a spherically symmetric function. And so the Laplacian is psi dr times 2r plus second derivative. That's spherically symmetric. There are two terms. So the guy that I want, because I take this and I multiply by the linear theory. So it's linear theory minus some k squared correction. K squared correction is r squared times this. This is writing the k squared in real space. These two terms, I can now ask, when is one 0 and when is the other 0? So let's ask, when is the first one 0? So that's the position of the peak, right? The maximum. So when this one is 0, then this one may not be 0. And in fact, if you look at the correlation function, where is the maximum is where you are maximally dropping down. So where it's most curved. So that's where the second derivative is big. So that's why the peak height changes a lot. It gets completely suppressed because this term is not 0. At the position of the maximum, this guy is a big correction. But now I can ask, what about the scale where this guy is 0? So that's what I call the inflection point. So where this one is 0, this one need not be 0. So now I can try to work out what is the amplitude of this guy. So the way I try to write this guy, there's one here, so there's the r squared. Then this 2r, the psi dr, I write as, I'm going to do the psi d ln r with r squared. So I'll do this scale, and this one is now dimensionless. So now this one is the r nonlinear series, it's the 7 megaparsec over the scale of the inflection point, which is the scale of the BAO, which is the 104 megaparsecs. So this is like cell over 100 megaparsecs squared. So this is a small correction. And so that's why the inflection point only gets a small correction. So that means that so long as gravity, the evolution, can be expanded as a power in k squared, the inflection point is always going to be more stable than anything else. And so it's a very generic argument that this should be the most stable.
It's not assumption.
Zeldovich is the assumption.
Huh?
Zeldovich smearing is the assumption.
No, apart from that, I could do just dimensionless of R. Somewhere, it's d psi by d.
Good. Yes, that's fine. So you want this one also to not be too big.
Yeah.
Fair enough.
As long as that is order unity.
Yes, that's right.
Not completely model independent, but maybe.
But this one, if you want, you can see the evolved version of this in the data directly. Right? So you can see the positions of the heights and see if they haven't changed.
Yeah, I agree.
Yeah. But you're right. So if you see a big slope, then you will start to get worried.
Yes.
It may be a way of already ruling out classes of modified gravity theories where this is no longer true. This term d psi d log r is already large, it's obviously wrong. Okay, so we are well over time and snacks away. So let's thank Ravi for a very nice meeting this evening, but for students who want to talk to him, he's around for a couple of hours.